So hello everyone! Well, today we're going to be covering our 14th lesson of thermodynamics, which is going to be reheating and intercooling. What is reheating? Reheating is, you might recognize this from the same process we covered apparently 14 times probably by now. So air comes in, compressor, goes to the heater, out the turbine. However, what reheating does is this turbine here operates at some intermediate pressure. So say this is P in, this is P out. This air leaves at P intermediate. And it does this because it's going to go into the heater again and then be sent through a second turbine. So this system actually works with two turbines, and the exhaust from the first turbine is sent back into the heating element, reheated, and then sent back out through a second turbine. And now, so the goal of this heating cycle can be to increase the temperature, for example, of state point 5, this is the state point right before it goes back into the turbine, to the same temperature as the initial state before the first turbine. But what it does is it increases the efficiency of your system because you're able to get more work out of the cycle. And now this type of part has to be you have to be careful, because when you use reheating, well, you're also adding additional heat. So there's like a fine line you walk between doing too much reheating. You're getting a lot of work, but now you're decreasing the efficiency of your system because you're just adding so much more heat, to that point where you're getting so much more work out that you're increasing the efficiency because you're just able to get more work out than the heat. Well, that's not true. You're able to get more work out than you would normally by just having one heating cycle. So if you recall, the heating or the work you get out of a cycle is the area underneath the curve. So if I were to just do the original cycle, this is the amount of work I would get out, this area. However, by adding the reheating part of it, I get all this additional work here out of my cycle. So now I'm able to get more power generation. But again, you're walking a fine line between being inefficient and being very efficient. So you just got to be careful. Same thing is going to also result from intercooling, but we'll cover that in the second half of this video. So first we're going to solve a problem. So let's write the state points out. State point 1, T1 is equal to 300 Kelvin. P1 is equal to 100 kilopascals. PR1 is equal to 1.386. H1 is equal to 300 kilojoules per kilogram. So state point 2, we're given that P2 is going to be 1,000 kilopascals. PR2, because it's 10 times more, is going to be 13.86. Go to the table, you can get that H2 is equal to 580 kilojoules per kilogram. Again, we're doing P1 over P2 is equal to PR1 over PR2. So let's do state point 3. We're going to heat the system up to 1400 Kelvin. Our pressure going into the first turbine is 1000 kilopascals. Our PR3 is 450, and our H3 is 1515 kilojoules per kilogram. State point 4. So at this point, we are leaving this first turbine, and we are right here. So we are told in the problem that P4 is equal to 300 kilopascals. So if we end up solving for PR 4 over PR3 is equal to P4 over P3. We get that PR4 is equal to 135.15, and that H4 is 1096 kilojoules per kilogram. So then let's go to state point 5. Well, we're going to run under for this example, we're going to run under the assumption that it is the gas after it leaves the first turbine is reheated again back to the original temperature at state point 3. Now, if I'm going fast through this section, don't worry, no math is being done right now, really. I'm just writing down the state point values that at this point, now we've covered how to do it. What lesson are we on? 14, so probably about 3 or 4 times by now. I think actually probably a little bit back at diesel, so I think diesel was at number 9, so maybe 5 times. But don't worry, well, once I write the state points down, we'll slow down. So T5 equals 1400 Kelvin. P5 is equal to 300 kilopascals, because remember, there's no compressor here. What leaves the turbine is being heated again and then pumped into the second turbine. So at this new temperature, we look up PR5, which is 450, H5, which is 1515 kilojoules per kilogram. State point 6. Well, now we're ejecting into the atmosphere. So P6 is equal to 100 kilopascals. By doing the same thing, PR6 over PR5 situation, like the ones we've done before, we get that PR6 is PR5 over 3. Which gets you 150. And H6 is 1127 kilojoules per kilogram. Okay, these are the state points. So, to reiterate, we're doing a reheating cycle. So here we have the air coming in from the atmosphere, going through the compressor to get to 1000 kilopascals. It is then pumped through a heating element, which heats it up to 1400 Kelvin. We put the air into the first turbine. It leaves at 300 kilopascals. It is reheated again and heated up to 1400 Kelvin again, and then sent back through the second turbine where it leaves into basic atmospheric pressure. And you'll get the extra workout because you're dealing with a second turbine. So, how do you analyze the efficiency of this cycle? Well, you analyze it the exact same way you analyze the efficiency of any other cycle. Efficiency is equal to work of cycle over Qn. Efficiency is equal to work turbine 1 plus work turbine 2 minus work of the compressor all over the Qn of the first heating element plus the Qn of the second heating element, but the second time. So heating, first instance of heating from 2 to 3, second instance of heating from 4 to 5. So using first law, like we've done multiple times before, you end up resulting in H3 minus H4 plus H5 minus H6 minus H2 minus H1 all over H3 minus H2 plus H5 minus H4. Alright, so we have our numbers, we have our things, let's plug it in. So what is the efficiency for this system? Well, it would be 1515 minus 1096 plus 1515 minus 1127 minus H2 minus H1, which is 580 minus 300. 80 minus 300 all over H3 minus H2, which would be 1515 minus 580 plus 1515 minus 1096. Your efficiency that you get out would be, plug this into the calculator, well, this gets you 527 divided by 580. $13.54, and you get 0.39, so you're at 39% efficient. Alright, well, that's not great. That's not great efficiency. This cycle should be improved very much. In fact, I'm going to go make sure I didn't type the numbers wrong into the calculator real quick. So, no, alright, 39% efficient. So this is reheating. It's just the exhaust from a turbine is being reheated again and pumped through a second turbine. You'd analyze it the exact same way you've analyzed any other type of problem that is dealt with open systems. One thing you will notice about your thermodynamics courses, whether it's however it's split up, when you're analyzing a cycle, it's the same. If you know the first law, you can basically do anything inside of thermodynamics, analyzing any type of system just by knowing the first law. Now, the other laws are important, of course, and you do need them, but if you have a good understanding of the first law, you can do any problem. Alright, so we're going to take a quick break while I copy down and get ready to explain what intercooling is. Thank you. Alright, so this is intercooling. What intercooling is normally when you have a process, such as this process up here, you have a compressor that will draw in the air, compress it, and then you heat it up. Well, what intercooling is it involves two compressors. So the first compressor draws in the air, then the air is cooled down. So here it draws in the air, and then the air is cooled down, and then it is compressed further in the second compressor, and then heated. And so what this allows you to do is it increases the temperature difference between the lowest point and the highest point of the heating cycle, so you add in more heat, and as a result you're able to get more work out. So by simply looking at this TS diagram, we see that this side here in blue is the normal work you'd get out from just a standard cycle. But this spot here highlighted in black is all the extra work you can get out of the system by including intercooling. And so but again, this would walk the fine line of if you're adding too many compressors and doing too much intercooling, you're removing more, or you're putting more work into the system, and so you're going to decrease the efficiency of the system, because even though you will get more work out, if you have to pump in more work, you can decrease the efficiency because it's work in minus work out, or no, it's work you get out of the system minus the work you put into the system, all divided by the heat you add. So now how would we analyze now let's do a quick state point thing just to show you how it's done. I'll write the efficiency for this, and then I will cover why intercooling and reheating are being covered at the same lesson. So, state point 1, standard, T1 is 300 Kelvin, P1 is 100 kilopascals, PR1 is 1.385, H1 is 300 kilojoules per Kelvin. Okay, so what about state point 2? Well, state point 2 is pressurized to 300 kilopascals. And then, so then if you do the P1 over the standard pressure calculation, you will get that PR2 is 4.155, just to be checked. Yep. And you get T2 is 410 Kelvin, and H2 is 411 kilojoules per kilogram. Alright, now I'm cooling it down again. So when I'm doing the intercooling, I'm cooling it back down to atmospheric temperature. So at state point 3, I am at 300 Kelvin. H3 is 300 kilojoules per kilogram. And PR3 is 1.385. Okay, then let's do state point 4. PR4 is, again, equal to PR3 times P4 over P3, which would get you 4.61, which means T4 is about 425 Kelvin, and H4 is about 425 kilojoules per kilogram. Alright, and so just for this turbine, we'll say state point 5, T5 is 1400 Kelvin, and the values are up here. If you need it, you can just simply rewind the video. And state point 6, atmospheric. Now, with all these state points, we're not going to solve a problem like this because we have solved these types of problems so many times. The point right now is just to explain the concept, because if I were to solve this problem, you're just going to get the exact same thing up here. So I'll write the efficiency equation for you. So, remember, is equal to the work of the cycle over the Qn. Well, the work of the cycle is the work of the turbine minus the work of compressor 1 minus the work of compressor 2 all over the amount of heat you pumped into the system. So, standard, do the math between get your enthalpies of each state point, plug it into the equation, you can get your efficiency. So, again, what intercooling is I have a first compressor that's pressurizing the air, then since you're pressurizing something, it heats up. I am cooling it back down, and then I'm pressurizing it again. This allows me to get the gas to a higher pressure and allow me to get more work out of the system when the air goes through the turbines. Now, you might be asking yourself, I don't know if you are asking yourself, now, there's a reason I am covering reheating and intercooling in the same lecture. It's because they both increase the amount of work you can get out of a system. Well, what happens if you combine them? Well, I'll show you what happens. So if I have a plot here, we're not going to solve a problem, by the way, because again, it's finding the enthalpies at each state point, plug it into the efficiency equation, you're done. But what we get, if say we were to have multiple stages of intercooling, is you just get this zigzag. And then if I were to have multiple stages of reheating, I would also get this zigzag up top. So this process where this would have been the normal work I would have gotten, I'm now able to get all this extra work up here and here. So I'm able to increase the work I get from I am able to increase the work I get from my system. But again, you have to be very, very careful when you're including intercooling and reheating, because you might end up heavily decreasing the efficiency of your system because you're pumping more heat in and you're requiring more work to be put into the system for it to get more work out. So it's a fine line. I've had it before on some of my projects where the difference was literally adding or removing one reheater and one intercooling, and my efficiency could fluctuate by about 10%. So you just have to be very, very careful. I hope so. This is our second to last video. Our next video will be on the Rankine cycle and combined Rankine and Brayton cycles. And then that'll be our last video on thermodynamics. That will be uploaded either sometime next week, either Tuesday or Wednesday. And then fluid mechanics is done as far as I know. If there's other topics that I see fit needed to be added, I shall add them. But our next main topic will be vibrational mechanics, and I will include some material science as well. Thank you very much. If you found the video helpful, please like and subscribe. If you have any questions whatsoever, please leave a comment. I'll answer them as soon as I can. Thank you very much and have a wonderful day.